folks. So welcome to our study of the chain rule. And I personally believe that the chain rule is one of the most important mathematical tools you'd ever learn in your study of mathematics. I mean, it underpins so many physical phenomena that is unbelievable. I mean, if you think of processes, from the making of toothpaste to the baking of a muffin. I mean, it's really nothing more than a composite process. So composite functions are extremely important. Why is it called the chain rule? And I like to say that, yes, it's differentiating what we would call composite functions. So on with the program. Very good. I'm all excited with this one. Just quickly review the concept of a composite function. So think of a composite function as a process, an operator. So you've got a set of elements, which we, in this case, we like to call the domain, or we could call ingredients. You apply some rule to that, which is, in this case, we label f, and the output itself is the rule applied to this set x to produce an output called f of x. So the elements in the output are called f of x, or from ingredients we have a process and we have, of course, the products. And we can continue with this process. So once we've got the new set f of x, that now becomes our new input or ingredients, we apply another function or another rule to that, call it g, and it produces a different output. So we can continue with this process, and you can see why it's called a composition of functions or a composition of applications or sub-processes. Of course, there are many rules that we are basically overseeing here, and that is, we're looking at, obviously, we're assuming that these functions or the domains are well behaved, they're well defined, that the rules that we apply are also well defined over the domain. So here's a pictorial sort of view of things. You know, we've got a function f of x, which is 2x plus 1. It's linear. And we now want to compose this. We're going to apply a rule to that. And the rule is what we're going to call g of x, which is x squared. So what it means is, if we take a g of f of x, wherever there's an x appearing in g, we shall now replace it with, so g of f of x is nothing more than f squared. So wherever there's an x in g, we replace with f, so that turns out to be 2x plus 1 all squared, which is exactly the output that we have here. So you can think of this as a process in a factory. You know, you have some sort of input, some sort of ingredient, and all you're doing now is you could be changing the temperature, you could be changing the pressure, and you could be adding another ingredient to that in a certain ratio to produce a final product. Okay, so the idea now. So let's just start off with a simple example. I've got two functions, f of x to be x squared and g of x to be x plus 1. And let's look at the composition f circle g. What does f circle g of x really mean? It means nothing more than, if you remember your notation, f of g of x. So what it means is, wherever there's an x appearing in f, you shall replace it with the function g. So that turns out to be x plus 1 all squared. What about g circle f? G circle f would be, take your function g, wherever there's an x, you will replace that with f. So it'll be f plus 1, but the function f is nothing more than x squared plus 1. Notice that the composition, f circle g, is not equal to g circle f. Something else that's more interesting, and now we have a triple composition. If you want to define that, we want f circle h circle g. Be very familiar, or very, very careful in how you apply the composition. So you always start off with the inside there. So let's try h circle g. That is nothing more than h of g of x. What does that mean? Look at h. There it's ln x. Wherever there's an x, we would replace it with the function g. So that becomes ln g. But what is g? That's sine x. So it becomes ln of sine x. So now we've taken care of the innermost one. So now we're going to go f circle. And let's call this composition capital X. So now f circle h circle g is nothing more than f circle x. And it tells you wherever there's an f in x. So wherever there's an x in f, we shall replace it with capital X. So that becomes e to the x, which is nothing more than e to the ln of sine x. And most beautifully, e to the ln of sine x is nothing more than sine of x. So you can play around with this and you can have lots of fun with this. And yeah, so knock yourself out. Go h circle g circle f, f circle h circle g circle h circle g, and have lots of fun. But more importantly, to me, derivative. Okay? Now I always say this, and I think in physics, and I've said this earlier as well, and that is, it's more important in applications to know the derivative of a function than the function itself. So think about a simple example like Newton's second law, F net equals to ma. I mean, there's an alternative to that law, a formulation of that law, and it says that the rate of change of momentum, linear momentum, is equal to the net force acting on the object. The rate of change of linear momentum, let's go back to that. That is dp dt. So if I plot a graph of linear momentum versus time, the slope of that graph, dp dt, the gradient, would give me the applied force or the net force acting on the object. So there are various cases in physics, in engineering, in biology, where the rate of change of a quantity is probably more important than knowing what the actual quantity is doing at a particular time. Okay, so we've studied basic rules of differentiation, and they are very simple rules. The constant rule, we know that ddx of a constant is 0. The power rule, product rule. Quotient rule always gives students problems. I mean, ddx of f over g, is g f prime minus f g prime over g squared. One doesn't know whether it's f prime first or g prime first. But these rules become easy to implement with lots of practice. So the new rule is the one at the bottom here. So you've got a composite function. How does one differentiate the composite function? I think that's very, very important. Okay, so we're going to get to that right away. All right, so here we go. Okay, so we're going to start all over again. So if I remember here, I've deleted all of it, and that's not good. So we need the pen. So start h of x. And we said h of x was e to the x sine x over ln x. If you want h prime of x, ln x constant, differentiate e to the x sine x minus, it's a quotient. We've dealt with the numerator, and we now have got to differentiate the denominator, and then it's ln x all squared. Now you've got to be very careful here, especially with the product. So we go ln x, watch the use of brackets. So using the product, I'm going to differentiate e to the x, that's e to the x sine x, plus keep my e to the x constant, and differentiate sine x, and that's going to give me cos x, minus e to the x sine x. And what is ddx of ln x? It's 1 over x, all divided by ln of x squared. And I'll leave you to tidy up and make this look pretty, because you can look at the numerator, you can pull out e to the x as a common factor, but just be careful, you can't just cancel things out. There's a ln x multiplying e to the x sine x, There's a 1 over x multiplying e to the x sine x over there. So yeah, take some time. Common derivatives that you must or should know. I've seen people that are so enthusiastic, they've got tattoos of these things. You shouldn't do that. So e to the x, you should derive ln x. And the one that I like to appeal to you to have a good look is d dx of a to the x is not a to the x. It's a to the x times ln x. Ln a. So be careful of that. And then I've got the other 6 derivatives, which I think you should master. And the first 3 are pretty straightforward. And suddenly, if you look at 4, 5, 6, you've got to be very careful, especially with 4 and 6, because they introduce a minus sign there as well. So it's important that you learn these up. They pop up all the time. And then if you look at the hyperbolic functions, and some of you would have come across hyperbolic functions, if you're in school, perhaps not. First year university calculus, yes. So first function we look there is not incorrect spelling for the school learners, but f of x is sin x. Sin x, would you believe that? Its derivative is cos x. If you look at the second one, the derivative of cos x is sin x. Unlike the trig where you have a minus sign, the derivative of tanh is sec squared x, not shrek, sec squared x. The derivative of cosec x is cosec cot. Derivative of sec is sec tanh. And derivative of cot is cosec squared x. So you notice there are no minus signs popping up when you come to the what we would call the hyperbolic functions. Maybe I should write this down, and you may want to learn more about these hyperbolic functions. Very, very important in terms of applications. Get started. I try to think of the chain rule as trying to peel an onion from the inside out. Peeling an onion from the inside out is a bit weird. Yeah, so you've got to tackle the inside function, think of the composite function, and move from the inside all the way out. And if you understand that simple rule, then the chain rule is straightforward. The other question is, why is it called the chain rule and not any other rule? So where does that word chain come from? How does it apply? So take a simple example, f of x is e to the 2x. Now we know, well, we should know, that if we have a function g of x, which is e to the x, then its derivative is e to the x. So the idea is when you're confronted with a function and you want to know its derivative, try to make it look like something you know. So I've got e to the 2x, which is different from e to the x. Can I make e to the 2x look like e to the x? And if I can do that, then I'm on my way. So one simple way to do that is say, well, let u equal to 2x. Right? Then what is du dx? Well, du dx is just 2. So this function that they've given us now, f of x is e to the 2x, and if I'm replacing 2x by u, then this function is now a function of u, which is e to the u. But we're still differentiating with respect to x. So if I want df dx, I don't see any x explicitly. It's now implicit. Df dx is now df du dx. Do you see a sort of chain that's forming? A chain? That's the reason why it's called chain. What is df du? If f is e to the u, then df du is e to the u. What is du dx? Well, it's 2. Did they give us u? No, they gave us x. So fine, if you replace u with 2x, that's our final answer. So if f of x is e to the 2x, then its derivative f prime is 2e to the 2x. Straightforward, nothing difficult about that. Let's try. And I think it calls for a change in pen color as well, just for excitement. F of x is e to the x squared. Make it look like e to the x. What is the substitution? Simple. Let u equal to x squared. So what is du dx equal to? Du dx is now 2x. This function now becomes a function of u, which is e to the u. That's what we want. We want to make it look like e to the x. It's just a label. So df dx is what the question is asking us. Is df du dx. Right? What is df du? Df du is e to the u. What is du dx? It's 2x. Did they give us u? No, we introduce u. So go back, replace u with x squared, and there you have it. That's your final answer. How difficult can this be? I'm going to pause. Think about that. It's pretty straightforward. Okay, let's try this one. This one is quite exciting. F of x is equal to sine 3x. The derivative of sine x is cos x. Can we make this function look like sine of x? Yes. Yes. Let u equal to 3x. So what is du dx equal to? 3. This function now becomes f of u, which is sine of 3. Whoa, not sine of 3u. No, not sine of 3u. It's sine of u. Excellent. So it's sine of u. So df dx is what the exam is asking, is what the lecturers is asking, is what the entire universe is asking. So df dx is df du dx. What is df du? What is the derivative of sine u? What's the derivative of sine x? What is the derivative of sine of q? It is now cos. And then in this case, it's going to be u. And what is du dx? It's 3. So this, did they give us u? No. They gave us 3x. And there's your final answer. This has got to be very, very easy. You know, I'm of the opinion is that the chain rule, for some people, it just overwhelms them. It's because it's the way it's taught. It's the way it's lectured to. You know, people just make a big thing out of it, like Einstein's theory of relativity. Only 6 people in the world were supposedly understood it when this theory was introduced to the world. Really? Really? I don't believe that. Okay. Sine of x squared. Whoa, we're going from 3x linear now to x squared. What will you let u equal to? Come, let's do that. Let u equal to x squared. Talk to me. So what is du dx equal to? What is du dx equal to? 2x. Yes, exactly. So this function now becomes f of u, which is now sine u. So what is df dx? In that df du dx. What is df? What is ddu of sine u? We know it's cos u. What is du dx? It's 2x. Did they give us u? No. They gave us x squared. And there's your answer. There's your answer. Whoa! Sine of e to the x squared. Where would we start? Well, let me try to grow this chain for you. And that's the reason why I put this example up there. Because, you know, we had a 2-member chain. Now I want to link it to 3 members. And then I want to go on to my own style of approaching the chain rule. So the first thing is the innermost function. That's what I like to call that. The innermost function is x squared. So let u equal to x squared. If u is x squared, then you got sine of e to the u. Not pretty. Sine of e to the u. Okay, if I let u equal to x squared, so what is du dx? Du dx is going to be 2x. So this function now becomes f of u, which is sine of e to the u. I still like it to look like sine x. So it makes sense to introduce a new variable. And that variable I'm going to call k. So let e to the u be k. So what is dk du? Dk du is e to the u. So this function has now become f of k, which is sine k. Follow me here. Stay with me. So df dx, let's peel from the inside out, is df dk. But k is a function of u. dk du. See, there's no x here on the right hand side. We need to bring in the x. But u is a function of x, so which is du dx. You see the chain growing up? Now we've got a three-link chain. So what is df dk? df dk would be cos k. Let's put them in brackets. What is dk du? dk du is e to the u. And what is du dx? du dx is 2x. Did they give us k? Did they give us u? No, they didn't. So we've got to go back to the original variables. Do not stop there and grin. That's not going to help the situation. So df dx is what the exam question is asking. That's where the marks are. That's where the money is to replace everything in terms of x. So 2x, u was x squared, and what was k? It was e to the u, so we got cos e to the u, but u is x squared, so e to the x squared. That's your final answer, and that's it. So now we've passed Maths 1, and now we can go on to Maths 2, and that's the beauty of this. It's not just a matter of writing and passing the exam. It's about understanding these rules at a fundamental level that even from 20 or 30 years from now, if I stopped you on a street corner, gave you one of these functions, said, differentiate, you should be able to do it. Do not learn to pass an exam. Let's get jiggy with this. Will Smith? Yeah. So the innermost function here, let's go. Ask the question. The innermost function here is sine x. Then you got e to the sine x. You got cos operating on that. And for the love of God, you got tan operating on that. And finally, ln operating that. My goodness, will you have functions like this in everyday life? Perhaps not. Maybe it's sitting somewhere in some quark content of space-time. I don't know. So let's go df dx. So df dx. Start with the inside function. The innermost function is sine x. Watch this and learn. What is the derivative of sine x? The derivative of sine x is cos x. Done. Boom. What's the derivative of e to the something? The derivative of e to the something is e to the something. You speak like that, and that's it. Next function is cosh. What is the derivative of cosh of something? The derivative of cosh of something, I'm going to say, is shine of that thing. What's the derivative of tan? What's the derivative of tan of something? Let's go. Tan of something. That's going to be sec squared of that something. Look at the brackets. Look at the brackets. They're all queuing up. They're all queuing up. 1, 2, 3, 1, 2, 3. And finally, what's the derivative of ln of something? Well, the derivative of ln of something is 1 over that something. And that something is the whole thing over there, which is 1 over tan of cosh of e to the sine x. Let's speak mathematics here. There's your answer. There's your answer. And you can make some simplifications here, because you got sec squared of cosh of e to the sine x. You got tan of cosh of e to the sine x. You know, sec squared is 1 over cos squared. Tan is 1 over tan is cot, which is cos over sine. So things can cancel out there, but you're going to be very careful when you're doing the simplification. I'm not interested in the simplification straight away. I'm interested in how you get each of these terms by going from the innermost function going all the way to the outside. So there's no need to make a u substitution. There's no need to make a v substitution. There's no need to make a p, k, whatever substitution. By looking at the problem, defining each of the functions separately and then differentiating them, you'd be able to produce the derivative. Hopefully you have one more. Yeah, there's one over here. Now this one you have to be very careful of. Take a look at this. What is the inner function here? The inner function is 2 to the x. Okay? So what is the derivative of 2 to the x? This is something you've got to go back to your calculus textbook for if you forget. The derivative of 2 to the power x is 2 to the power x times ln 2. It's not like e to the x. It's 2 to the power x times ln 2. What is the next function operating on 2 to the power x? It's sine. What's the derivative of sine? Derivative of sine is cosh of that thing. Next function is ln. What is derivative of ln of something? We all know it's 1 over that something. And finally, what's the derivative of tan of something? Well, the derivative of tan of something is sec squared of that something. And you look at these things and you just forget the number of brackets, but that's your answer. You can go and simplify that because you straight away over here, look at this and you'll notice if you're an elegant person, then your cosh of 2 to the power x divided by sine of 2 to the power x is tan of 2 to the power x. So that tallies up quite nicely and it compactifies your answer. But at the moment, let's write that down. Let's write that down. You agree with me that this now becomes cosh over sine is going to be tan of 2 to the power x, and then finally we multiply this out. You're going to get sec squared of ln of sine of 2 to the power x. There's your answer. Beautifully done. Nothing confusing, nothing difficult. It's just like when you were in grade 1 and they asked you what is 1 times 1 and you gave the answer. And it's 11 times 11 and you gave the answer as 121. Simple. Keep it simple. Whoa, look at this one. Is it really worth doing this? Yes, it is. And the reason for this, and this is as bad as it gets here, is that you got sine of x over e to the x, so that's a quotient straight away. You have a product over here. 2 to the sine x, very interesting. Cosh 2. What is ddx of cosh 2? Do not tell me it's sine 2. Cosh 2 is a constant, so ddx of cosh 2 is 0. So let's go w prime. Let's do this. And watch the way I write this out. So you start with the inside function. The inside function is x over e to the x. Now, don't try to be a genius and try to do the quotient at one go. Write it as prime. What is ddx of sine of something? That's cos of that something. Agreed. Minus. There's the product. Do not try the product immediately. Write it as a prime. And what is ddx of ln of something? It's 1 over that something. What is ddx of 2 to the sine x? Now here you've got to be very careful. We know that ddx of 2 to the x is ln 2 times ln 2 times 2 to the power of x. So we start the inside function is sine x. So what is ddx of sine x? Ddx of sine x is cos x. Now we ask ourselves, what is ddx of 2 to the power something? ddx of 2 to the power something is ln 2 times 2 to that something. Take some time, have a look at that one very, very carefully. And of course, ddx of cosh 2 is going to be 0. So no contribution there. Let me just put a big fat 0 over there. Now start to expand the quotient. So here we're getting some. So it's e to the x, ddx of x is 1, minus, keep x constant, differentiate e to the x. And this becomes e to the x all squared. Put a bracket over there. This stays as cos of x e to the x quotient minus bracket differentiate x. You're going to get 1. Keep cosh of x squared constant. Now it's plus because it's a product. Keep x constant. Now here you've got to be very careful. ddx of cosh x squared, the inside function is x squared. What is ddx of x squared is 2x, 2x, and then ddx of cosh is sine of x squared. Messy, but fine. Do not forget the denominator. And then finally we got this last term over here, which is plus cos x, and then it's this bracket in there. That's what the derivative is. You can start tidying up, looking for common factors. For instance, if you look here, there's an e to the x as a common factor, and we can start writing this out. Let's write this in this green. At the top, I can take e to the x as a common factor. That'll cancel out. Please follow me on this and check this. I get 1 minus x all over e to the x. This whole bracket collapses to that. Then multiplying cos of x e to the x. So that's done. Can we do anything in here? We have a cos x squared. We have an x squared. Not really. So here we can say minus, again, bracket, cos of x squared plus 2x squared sine of x squared all over x cos of x squared. Follow me. And then finally the last term is going to be, I like to put the constant out here, ln 2 times 2 to the sine x times cos x. That's your final answer. You can double check that for me, but I think this is a really good example. I mean, if you can get this right, then the chain rule, it's done, dusted, and you can put that to bed. So, having been through the entire thing, you don't have to make those substitutions, u, v, w. If you're getting into it, maybe at the start, you can do that. But start off with the inside function. Try to peel the onion from the inside out, and you would have no problems with it. So thank you very much, and I look forward to introducing you to implicit differentiation as well as logarithmic differentiation. Excellent.